I'm in this conversation an awful lot, so happy to bring that to you. I'm going to go ahead and share my screen.
And also a quick warning, everyone, we are planning on recording this session for future watching privileges, so just want to make sure everybody is aware of that.
That's great. I appreciate that. Now, so as I've got this screen shared, Brittany, I won't be able to see the chat, and so feel free to jump in if there happens to be a question. If somebody wants me to linger on a particular slide or a topic, or ask a question that you want me to answer, feel free to do so. And Brittany, if you wouldn't mind jumping in, that'd be great.
That sounds good. I think Katie actually also put your slides in the chat as well if people want to go ahead and download that file.
I did see that. Great. Yeah. So just a little bit about me. Brittany did a great job with the CV that I gave her. Some of my background, I'm an architect by education. I've got a Bachelor of Architecture from Iowa State University. More importantly, though, I've been in the concrete industry for 30 years. And at first, it was working with engineers, working with architects in terms of system design, system delivery, a lot of construction education with a manufacturer in the insulated concrete industry. And then the last 20 years, I've been managing concrete associations. My firm, you see the acronym there on this slide, SB2, Sauter, Baty, and Bloomquist Incorporated. We're second generation of a firm that began managing the Tilt-Up Concrete Association and the Concrete Foundations Association way back in 1992 and 1993. I'm currently executive director, as she said, of CFA, Concrete Foundations Association. You've got that website there. And I think, especially in terms of relevance for today's presentation, I think I certainly have a wealth of background in working with these two concrete industries. One's cast in place, one's largely residential foundations, some commercial foundations, some slab work. And so I get a unique perspective on concrete cracking there. And then the other side is in the tilt-up industry, which is site cast. Precast would be another way to look at it, or if you're from Texas, you call it tilt wall. And there is always cracking involved in that industry. But then my participation in ACI, and you see some of the committees that I serve on, ACI 332 Residential Concrete Code. I was the chair for the first three issues of that code, and I continue to work. And most relevant, again, I think, with this topic is my current chairmanship of ACI 380, which is the new plain structural concrete committee for ACI. It picks up with the work that ACI 322 did back in the 60s and early 70s, was actually folded in 1972 as ACI 318 took on the provisions that committee had been working on and introduced it to the structural design code. So a lot of background, a lot of opportunity for me to kind of set the stage for what we really want to talk about. The two associations that she mentioned in my relationship with, we do manage the Tilt-Up Concrete Association. I handle all of the technical and regulatory affairs for this industry. So again, I get to interface with those that are on the frontline design, frontline construction. I am also the primary certification instructor for this industry for tilt-up certification. Some people have called it the basement dweller industry or basement dweller association, but it really is cast in place concrete professionals working in relationship to the International Residential Code. So what we're going to talk about over the next however many minutes, I'll go until you pull the shepherd hook out and get me off the stage. We're going to talk about cracking in particular. And so I use that headline or the title of this presentation quite a bit in all of my presentations, whether I'm teaching certification, whether I'm educating architects on what's available and what opportunities are out there for concrete. When I talk to real estate agents and help them see how to evaluate concrete systems, we always know the three truths of concrete. It's gray, it gets hard, and because it gets hard, it inevitably cracks. And as structural engineers, you rely on its cracking because that's what gives you well over half of your design work. Those of you that work with concrete, is the fact that it cracks. And so because it cracks, then there's the whole steel reinforcement. And then today we're also getting into glass fiber reinforcement products, random reinforcement or three-dimensional reinforcing. So there's a whole nature of the industry that relies on the fact that it cracks. But ultimately why we're here is because cracks become problematic, and it runs the gamut from aesthetic to structural problems. And so I've kind of broken this presentation up into 4 key areas, and we'll loosely follow our time talking about some crack patterns and common causes for those cracks. We'll talk a little bit about cracking concerns then. When we do see a crack, or when someone sees a crack, what is the concern for it? What might we assign associated concerns with those cracks? And we'll look at some plausible solutions and some of the solutions that I've seen come out. And then I'm going to go a little bit deeper into this 3 areas that I have primary responsibility for, which would be slabs, below grade walls, and above grade panel construction. And then I'll leave you with some common industry references. So if you want to read more, if you want to rely more on some resources, those will be towards the end, and you'll be able to put those into practice. Why we're here is because concrete is the most widely used material in the world after water. So water's in everything. We know that our bodies are some 92% water. And aside from water and the use of water in everything that we do, concrete, and particularly in terms of built construction materials, concrete or cement, I suppose you could say, you could back it up to the raw element, is the most widely used material. And so we're looking at 2 really iconic images of concrete here, the Sydney Opera House and the Hoover Dam. And when we see concrete, our eye generally is going to do 2 things. It's going to respond to the beauty and the fantastic form that concrete emotes and embodies, or we're going to have our eyes drawn to the quality control issues. We're going to see the small bug holes. We're going to see the differences in the forming techniques, or where the form breaks were, and we're going to see concrete and where it cracks. It's interesting to me to think about the history of concrete. On the left-hand side, of course, Falling Water by Frank Lloyd Wright, one of the most documented concrete residences that has had repeated cracking issues time and time again. And it's gone through 3 different renovations to try to repair, reinforce, rehabilitate, and mitigate the future of cracking in that iconic architecture project, regardless of whether it was built with concrete. And on the right-hand side, for comparison, built between 600 BC and 800 BC is the Pantheon Dome, and you can see the oculus there. And this is an unreinforced concrete structure. The former director of the CFA, who was my business partner for a lot of years, he and I were having dinner last night, and in that setting, we were still talking about the chance to get to visit this structure. And so it's still in operation today. And that's staggering to me to think about concrete and the longevity of its behavior and its performance, and yet cracking is what we're going to focus in on, and the fact that cracking does happen, cracking causes problems in today's concrete. So let's go into distinguishing some crack problems and some patterns and some causes. Now, this is not what we're going to be talking about. You guys are all structural engineers, and I'm going to leave it to the professionals in the room that understand the nature of structural fatigue and structural cracking. In general, I would offer to you that when cracking becomes a problem, a project problem, it almost never is cracking like we're seeing here, or it's almost never cracking that is going to cause concern for structural. Now, a homeowner may say, hey, there's a crack, I'm worried my house is going to fall down. But that's not the same as an engineer looking at it and knowing instantly that's a problem that we have to address right here and right now. What we're going to be talking about is more the in-between segments of cracking and maybe the finer side of cracking. Before I do, I want to talk about concrete materials, because it's the nature of the concrete material that causes most of the cracking that we see. And so we know that concrete is a very basic. One of the reasons why it's the most popular, the most widely used material is because it is so basic and it is so local. It relies on Portland cement, which is the powder, and everybody in the concrete industry hates it when they're at a meeting of a local school board or a city council meeting and somebody's talking about the cement driveway or the cement sidewalk. Cement's the powder, concrete is the hardened product, and it is because the cement gets mixed with large aggregate, small aggregate, the water itself, some admixtures in today's world because our technology is so great, and you see the product sliding down the chute there and into the delivered form is a nearly high viscosity, seemingly fluid mixed in with some space making materials. Once the water is introduced to the cement, we realize that there's a chemical process that takes place, and the concrete begins to instantly transform. The chemical process is hydration. Any chemical process has a byproduct. The byproduct of hydration is the heat. And so we could go and spend another 2 hours or 3 hours just talking about the behavior of concrete and its benefits from a heat generation perspective. But that's also a characteristic that begins to set the foundation, if you will, or the baseline for why we're talking about cracking today. And so we rely on these crystals. This is a microscopic view of hydration, and it's fantastical. This is the stuff of science movies, science fiction, and you can see and think about these crystals beginning to envelop everything within the mix. So it might be a structural embed that you've designed to connect a panel or a foundation element to another part of the building. It might be the aggregate itself. It might be the reinforcement, but these crystals begin to grow, and they are quite voracious as they consume the water and begin to develop the strength. The strength comes from these crystals that connect everything together. So concrete needs three things. It needs water. We know that. We just said that. It's a chemical process, a reaction of the cement to the water. It needs temperature. So in other words, if we cool a concrete down, and certainly if we let it freeze, hydration will stop because the water becomes a solid. And if the water is a solid, it can no longer react with the cement. So concrete needs temperature in order to mature or to gain strength. It also needs time. The longer we give it, the stronger it's going to get. We know that because you as structural engineers will specify a 28-day strength for the type of concrete you want on a given project. And yet a contractor might be looking at the 5-day strength or the 7-day strength. Or maybe it's an elevated slab that they've been heating to try to increase its maturity more quickly, and they need a 3-day strip. And so time is an element that is very important to what we're trying to get out of the concrete from a strength perspective. Some ideas of time and moisture combined here. This is a graph that just shows you 4 different mixes taken into the laboratory. They're all 4 of them are designed with the same target concrete strength of 28 days. And if from a structural design perspective, you can see the laboratory air. If we just take the cylinder, we bring it into the laboratory and we let it sit there for the duration, we test it at 28 days. You can see that's the yellow line right in here. It's going to level off, and then because it's in laboratory air, which has a relatively low relative humidity, it's going to actually be pulling moisture out of the concrete cylinder or out of the concrete curing, which is then going to slow its opportunity to gain, and it'll level off, and after about 90 days, it will no longer gain any strength. It doesn't have any more water available to it. If we keep it in moist curing environment for 7 days, instead of just putting it in the air, you can see that the 28-day strength is greatly enhanced and will go almost another 1,500 psi on this particular curve in the 28-day strength, just because we give it moisture early on in its age. If we're able to cure it in moist conditions, keep the moisture around it for 28 days, we're a little bit higher even. And particularly once we get out to 90 days, beyond the 28 days, you can see we're extending that accessibility, taking longer for the moisture to either be consumed or to evaporate from it. And then if we're able to keep the whole time, and so this would be like your bridge columns, bridge piers, the backside of the Hoover Dam. that concrete is constantly adjacent to moisture. It has a perpetual source of water. And so we know that regular concrete, normal concrete that you're designing, it never sees its ultimate strength because we pull the moisture out of it. If we keep moisture there, there's always going to be some cement. Think of it at the nanoparticle level. There's always going to be cement to hydrate and react and grow more crystals. And so this just gives you an idea of how effective moisture is. Well, that means in order for us to really do what we need to do, and we'll look at some slab cracking examples, but if we want to control the behavior of the concrete, think of concrete as an animal. If we want to control that animal, the best way to do it is to keep moisture present. Well, the bigger that it is, the wider it is, the larger the square footage, the harder it is. And so you see a contractor out here putting some water down over the concrete after they've gone ahead and floated it and finished it off, and then they're going to put a fabric over it, and this would be a water barrier fabric that's going to keep that water in on top of that slab surface to help give it that moist curing environment. Try to get another 3 or 4 or 7 days out of its curing before the water is completely consumed or evaporated. Similarly, temperature, right? We talked about temperature being one of the big 3 components. And so this graph just shows you the same concrete strength cured at 3 different temperatures, 90 degrees Fahrenheit, 73 degrees Fahrenheit, and 50 degrees Fahrenheit. And you can see that ultimate strength may or may not be affected. There's certainly a kind of a cap to it on this graph for practical reasons, but it's more about the delay. And so the colder concrete is, the slower it's going to gain strength, which is important. And it will negatively impact construction schedule. But we're talking about it from a concrete cracking perspective. And as we look at some of these examples, the importance is that the delay extends the behavior of concrete and lessens the behavior of cracking. So we become less concerned for cracking the slower it gains its strength, because we're consuming water at a slower rate, and which is also controlling its dimensional change. So one way we protect concrete and curing and keeping the temperature there, you guys are throughout a market that, like Iowa, is affected by cold weather. And so this is not an uncommon scene out on construction sites during the winter, is putting thermal blankets out or straw on footings, or maybe even putting a tent up and using some external heat to keep the temperature of the concrete buoyed up so that we can control its maturity, its strength gain. We can also, on the other side of it, get into the summer months, and we're trying to slow that heat gain down, because 100-degree Colorado day with the sun beating down on it, as dry as your environment is, your climate is going to suck that moisture right out of the concrete, which is going to mean the strength is it's going to get to its finite strength cap, or its ultimate strength cap, more quickly, but it's also going to dimensionally change more quickly. And that's what we're kind of setting the stage for as we begin to look in on cracking. So some of the things that we know, again, kind of the framework for what we're talking about. Of course, you specify a concrete in terms of PSI, pounds per square inch. Compressive strength, typically the range that we deal with in most of these construction industries is a 2,500 PSI baseline, maybe up to about a 5,000 PSI. And if you talk to ready-mix producers today, they're really targeting in at a minimum of 4,000, and a lot of them are producing 5,000 PSI, because they know if they deliver a little extra concrete strength, that it handles some of the problems that are closely associated with mixed performance, excessive moisture, added water on the job site for viscosity and flowability, maybe even the concern that a concrete's going to crack and they're going to get the finger pointed at them because it didn't get to the strength that was specified, and so they give a little more to it. But when we talk about why concrete cracks, I want to focus in on that middle one. It's tensile strength. We call it the modulus of rupture. It's only about 10% of its compressive strength. So if you look just at those numbers, it doesn't matter if it's 2,500 PSI or 5,000 PSI concrete. The modulus of rupture is really only 250 to 500 at a 28-day strength based on those specification design. And so the modulus of rupture is relatively low. And so if concrete is weak in tension or flexural crack resistance, that modulus of rupture, meaning if we apply pressure perpendicular to its structure, it's going to fracture at a very low strength. And so that also means that we have to be looking at the things that are setting itself up for how that crack, the stress that happens in the concrete that ultimately develops the cracks that are brought to your attention or brought to my attention, and everybody's concerned about them, and they're unsightly. What are we going to do about it? So let's take a look at why that happens. So here's 4 different mix designs, and we teach a lot in the certification side of my my duties, both for foundation certified foundation technician as well as tilt up technician and supervisor certifications. That the mix design varies greatly. There's going to be a target mix design that is most often specified, particularly so for commercial projects, less so for residential. Although a lot of contractors and ready mix producers kind of do have that specification that they like to use. But here's 4 different mix designs. You can see the cement is varied between 7 and 15%. The fine aggregate is going to vary between 24 and 30%. The coarse aggregate, there's a lot of variation there, between 31 up to 51%. And then there's this character in the middle of the water that we talked about that is ranging from 14 to 21%. And so what we're targeting there, what's interesting to me is that we try to optimize what we call the water cement ratio, water cementitious ratio, now that we use a lot of supplementary cementitious materials. And you can see that mix 1 and 3 they're both 15%, mix 2 and 4 is both 7%. And yet the water is going to vary. Well, if I'm concerned about the water to cementitious ratio, and I'm trying to maybe keep that as close to 0.45, maybe even 0.4 as possible, why would I have some variation, 3 degrees here, 4 degrees there? And then we take this mix. So there's 100% of my volume represented in all 4 of those bars. I move them out to the job site, and I give one of these mixes to contractor A, and contractor A gets mix 1 with 18% water and 15% cement and is going to pump it. And so contractor A puts in some high range water reducer, maybe a mid-range water reducing admixture, because it gives a better flowability within the concrete pump, and they know enough to not add water. And so they get that mix placed in there really well at that slump ratio, or that water cementitious ratio. Contractor B gets mix 2. And there's a higher rock in it, and it seems a little stiff. It comes out, maybe it's a 0.4 by the time that the contractor gets it. The ready mix producer maybe held back a little water, so there's a one-time addition on the job site. And what does that contractor decide to do? He starts telling the ready mix producer, the truck driver, add more water. And so they add 6 gallons of water. Then they add another 2 gallons of water. Pretty soon, my 100% volume there goes from 100% to theoretically 110, 115, 120% volume, and it's all being expanded by water. I'm not adding aggregate, I'm not adding sand, I'm not adding cement. Where concrete cracking comes more often than not is because of that water, because we're eventually going to take the water out of it. So whatever percentage we've got in the mix associated with water, we're going to lose. That's also in volume, dimensional change. And so 14%, maybe 14% of the 14% water in mix 2, let's say we don't add water to it, we're going to consume about 60% of that by hydration. We're going to lose about 40% of it to evaporation. And then depending on how well we control the moisture content, we could see that change either way. And so then you could say 100% of my volume size, my dimension size, if I consume the 14% or lose it, now I suddenly go from 100% to 86%. And that's where we begin to set concrete up for the type of cracking that most often is the callback or the concerning call that we get. And it does change based on a lot of these variables that you see there, particularly evolution between hot water and cold water. And so we know adding water happens. Adding water can be a good thing. Adding water could be a required thing, as I said, if we hold back water on the job site. But also, if we add a gallon of water for every cubic yard of concrete, we're going to increase that slump 1 inch. And you can see what's happening in this mix, in this photo. The large aggregate is already starting to separate, and the water is pooling the cement away from that aggregate. And so if we don't vibrate it very well, we're not going to get those constituents back together into a healthy mixture within this volume. When we do adding water, you can see a lot of the disadvantages to water adds. And so I speak to contractors about this all the time. It's a rigorous part of our certification is controlling water. But down here at the bottom, the two things that are most important to me, actually three, it's the poorer bond between the concrete and the reinforcement, the increased drying, shrinkage, and cracking, and the greater volume change. And so those are the three things that are setting us up for cracking. And what do we get? We get cracking of all kinds of natures. So here's a porch stoop slab. And in this particular design, you might expect a frost wall around the perimeter of this slab, and then they poured a concrete cap after they backfilled it, and let's hope that they engineered it and put a nice subgrade aggregate underneath there. And then they placed this concrete and really felt like they did a great job. It was a beautiful looking surface that they left for the homeowner. And the next winter, they get a call, actually coming out of after the winter, the next spring, they get a call from the homeowner saying, I've got this huge crack across this porch stoop. What caused it? What are you going to do about it? And so we know that those that's a classic example right there in a horizontal plane of horizontal cracking coming from shrinkage, the volume change. And I'll be willing to bet anything on this particular case, the contractor used a high water mixture, a high water cementitious ratio. They were probably either wheelbarrowing it in or they might have been direct shooting and wanted to make sure it flowed in there well. And it probably didn't have a high constitution of aggregate. And lo and behold, as that concrete tried to dimensionally change, it's anchored at the left side there against the brick wall. It's anchored on the opposite side. We're looking in on the short side, and it just tore itself apart. So when we talk about modulus of rupture being 10% of its tensile strength, if you add up the stress that's created by that element trying to shrink, you can calculate exactly where a crack is likely to occur based on what the modulus of rupture is applied to the cross-sectional thickness of that slab. And I've done that numerous times on sidewalks and driveways. Looked at an unjointed or no construction joints or no control joints put into them and been able to go out and predict where those cracks are going to occur. Now, they also may come from settlement, but here we've got no displacement on the two sides of the crack, which is a clean indication of a shrinkage crack. Here's another one. This is a vertical wall. And this vertical wall crack that you can see, we're looking right at a form joint between two cast in place form panels, and then a crack that loosely follows that form joint running up or down the wall. And so again, the nature of these cracks, homeowner goes down, maybe the homeowner's trying to finish the basement, and what do they see in addition to the crack? And you can kind of see it with these tan lines that are coming off that. That's soil residue. Moisture's been coming through that crack. And so it's an indication of when a crack is problematic, and we'll be talking about that throughout because we're getting moisture coming through that crack. In general, this is a shrinkage crack. And so shrinkage cracks, because the wall ideally should be reinforced, although for the better part of 50 or 60 years, even the International Residential Code did not require any reinforcement, any horizontal reinforcement in residential concrete walls. And so there was nothing really holding that wall together, that crack together. And so if there's nothing holding the crack from getting wider or from slight minuscule to the eye displacements, it's going to start leaking. And it leaks from additional water pressure in the soils outside, any changes to the drainage, if drainage is present, changes to the grade as settlement occurs, as well as applied loads. Maybe somebody is parking a camper out on the backside of a wall in the backyard, and they don't realize the load of that camper on the ground can start to push in and create some changing conditions to what the design initially had accounted for. Here's another type of crack. We looked at horizontal and vertical shrinkage cracks. Now we're looking at what we call a reentrant crack. And this is probably one of the most common cracks, particularly when you're dealing with geometry-based cracking or vertical sections. Although we see them a lot in horizontal planes, typically contractors do a good job of making sure that they cut a joint in a slab related to that reentrant corner. But a reentrant corner is basically any time you see an interior corner to a concrete mass, or where the concrete kind of turns at 90-degree angles on itself. And that means that there's going to be shrinkage stress. If you can imagine those two sides, so we'll call this side 1 down below the window and this side 2 up high on the window. Down below the window, it's part of the wall that goes to the left off that window. And so there's shrinkage forces that are trying to pull that concrete to the left. At the same time, all the way up above the window and to the right, that higher wall section is shrinking at a different rate off to the right. And where's the weakened plane? It's right there at that corner. And so often we see contractors not putting any reinforcement that will control or prevent, well, first of all, prevent that crack. But ultimately, there is probably a microscopic crack that ensues, and it won't control it. And so then you see the crack begin to propagate downward, and it's going to always continue until it finds relief. It won't find relief until it gets to the end of the mass. And so a very common segment of cracking. Other cracking is can be associated. So those are all three shrinkage crack options. Another common form of cracking is applied load cracking. Now this gets a little bit more into structural design issues, although I will tell you that particularly these two cracks, and we'll look at some other examples of it later on. These are means and method cracks, because the structural engineer does not design this condition. You've got a footing that's got a crack in it, and you've got the panel above that has some evidence of cracking that has come from that as well. And so you've got a footing that's settled. The reason the footing settled is because of the length of time that this particular concrete panel set on the footing without 100% bearing. And so typically in any kind of a vertical application, certainly cast in place wall, but in precast and tilt up panel constructions, the structural engineer record is designing continuous bearing. There's a period in time where the contractor has to support this on temporary, you can see them right in the middle there and off to the left side of the image, shim stacks or temporary supports before they're able to fully grout. And that puts a lot of stress. In fact, 75 to 80% of the building load for a tilt-up building or a precast building exists on the footing the moment that the concrete panels are set. And if the footing is not designed for that point load in terms of longitudinal reinforcement and width affected by the soil capacity, then cracks are going to happen. And so we teach to contractors the urgency of starting to get some additional supports in there and ultimately get into some grout, 100% grout placement. There's another nature of cracking that happens immediately. And this is probably one of the more problematic cracks from an aesthetic perspective and from an odor satisfaction perspective. It's called crazing cracks. It's caused by capillary shrinkage. And so if you can imagine this floor slab, we've just placed the concrete, we've got it all floated off, it's got its bleed water that's risen to the top, and then we're in Colorado and the winds are blowing and the sun's out there and it's baking that concrete. When the top of the concrete slab or the top of any concrete element, but particularly in slabs, begins to dry faster than the volume itself and the thickness of the element, you're going to see these crazing cracks develop. And this is where the surface tension is created within the concrete slab section, and it begins to pull itself apart. And it pulls itself apart in that upper half inch of the section. It's based solely on high evaporation rates. So this is where you see in the more arid climates and the warmer climates, like the photo I showed you earlier with the construction worker that was spraying water and then rolling a fabric over the top of it, trying to keep that water in that surface that is so easy to pull it out of the concrete. Give that concrete a chance to mature, because there's no way that the top surface of this slab can achieve its modulus of rupture, the designed 10% of compressive strength, when it doesn't have the aging on it yet to get to that strength. And so that crazing crack is really easy to pull the surfaces apart. From my seat, one of my common inquiries is the pour line. And pour line is, I get it at least a dozen to 15 times a year. Why do I have this diagonal to horizontal crack in my foundation wall? And you can see a pretty good representation here. That's a pour line. It's not a crack. I always throw it in there, one, for a bit of a levity in the conversation, but it also is a reality. We're conditioned to look at the inconsistencies, the abnormalities of our concrete when we see them, particularly if you're the owner and you've invested in this. And so this looks like a big old problem waiting to happen. Is it? Probably not. Particularly so if proper vibration techniques were used to make sure that we got some constitution between the two different timings of the placement. But ultimately, this is set up because one load was finished off and it was kind of allowed to run itself down almost to a self level. And then we came back with the second load, and maybe it took an extra 10 minutes or 20 minutes to get to the job site. And so you started to get some color change there. That'll never go away. You'll always see that little line there, but properly vibrated, it really isn't a problem. It only becomes a problem is if it turns into a construction joint where that lower section hardens, the upper section never really got fully bonded to it, and we get some leakage through it. Okay. Brittany, let me just check on any comments, questions that we want to get to.
I don't have any in the chat right now.
Awesome. Thank you.
I'll let you know if someone ends up typing one soon.
Perfect. All right. So cracking concerns and solutions. So when is a crack a concern? As I've said over and over and over again, I think the number one reason why crack is a concern is because it's an aesthetic influence on the expectation. So we teach a lot in tilt-up certification about the idea of mock-up panels and how important it is to deliver a mock-up panel that is as close to what you think you're actually going to be able to deliver as possible, which is not a bad thing to try to figure out if you can get a crack in that mock-up panel intentionally, because they're going to be there. But the aesthetic influence of a crack is certainly one of its number one reasons why cracking is a concern. It's why you get called in. It's why I'm presenting to you today, is because somebody over repetitive times in each of your careers has said, hey, I see that crack. Tell me more about that. Why did it? I thought you reinforced it or designed the reinforcement so that wouldn't happen. Sometimes they're unavoidable. The second is leaking. If a crack leaks, if you're trying to prevent climate control, or you're trying to provide climate control from the exterior to the interior, and you get leakage, that's definitely a problem, and cracking could be a huge concern there. Displacement may or may not be a structural concern. Displacement could begin to indicate that there's some movement on one side or the other of the crack that could begin to show some structural fatigue. At the very least, once we get displacement, where we do have steel in the wall, if we don't get that closed up or protected, we can start to get corrosion in the steel reinforcement. And then we all know what steel corrosion does to concrete. Structural risks are the ones that we're most often concerned about. And I've got I call it a funny example. It's not really all that funny, but this is certainly an extreme example of concrete cracking on the left side, because they did not backfill underneath that garage slab nearly enough, and they also got settlement and erosion underneath as some water removed through this garage slab that pulled the soil out in a step down footing condition, so they lost all of their support. Which is why so many garage slabs, even with full backfill, could be or should be designed as structural slabs to eliminate that particular concern. But the other thing that we really key in on is that when you see a crack develop, most of them, or almost all of them, are less than a credit card thickness. And so if a crack width opens up to about 1/8 of an inch, that's when we really start to get concerned that the cross-sectional performance of the wall may be sacrificed at the very least for water leakage, if not for something more than that. So let's look in at some different, some other different cracks. This is a horizontal crack in a wall. This is a big flag for me. Now, it's not a pour line, but as I'm looking at conditions that get sent in to me, doesn't matter who it comes from, most often it comes from homeowners, and I'll see this horizontal crack, and I'm really attentive to the horizontal cracks. I want to know more about the stability, the vertical stability of that wall. In this case, this is a foundation wall. I want to know if there's any evidence of bowing. Now, there's a difference between bowing and out of plane. Out of plane could have been created just by the wall being out of plumb when the contractor placed it. But we want to particularly look for bowing. We want to look for evidence of dimensional change, deformation, or displacement on each side of these cracks. Because once we get this crack in place, as you may know, we're relying fully on the reinforcement for structural performance. And steel's quite ductile. And once I start to get a horizontal crack with a load from the outside, and that pressure is a combination of soil and moisture, as well as maybe some applied loads at the grade level, the steel itself may not be sufficient to control the bending moment that's applied into that wall. And so we want to be very careful about the types of horizontal cracks that we're looking about. Here's a crack in a slab. And I've enlarged this to really look at the crack itself. And you can see the joint cuts by the contractor. And as nice a job, although that's a pretty messy, the slab joint that's going vertical there is kind of unraveled. The timing was a little late on that crack, but the horizontal one's really nice. And yet, as nice as that horizontal crack is, look at what the concrete decided to do. So what does that tell you? It tells me, first of all, that they didn't go deep enough with their slab joint. And you can kind of tell that based on the dimension of that horizontal joint. So when I get a chance to look at slab cracking, in particular shrinkage cracking like this one evidences, I'm going to look first at the slab joints. Where were they? Were they close enough together, or did they stretch them out? Very rarely am I concerned about the reinforcement in the slab, because contractors almost never get the reinforcement in slabs right. But I want to look at how deep is that cut. If that cut was deep enough, that crack should have never happened. But what happened in this particular case is that concrete, that slab joint was just far enough, and it wasn't quite deep enough. And so the modulus of rupture of the concrete was sufficient that the crack ended up right here. And it probably initiated right here where it had friction hang up with the adjacent slab section, and then it began to work off to the left until it raveled up and found the horizontal joint that we're looking at, and then it probably cracked and continued on across that. Now, is that a big problem? It is if it's a homeowner and paid an awful lot for that concrete. Particularly if it's a decorative concrete slab, but it could also become a safety or trip hazard. You see a little section, a little triangle of concrete that's broken away there, because we're going to get moisture down into that crack, and it's going to freeze and thaw and freeze and thaw. And then we're going to get our super salts, the mag chlorides and stuff that we're nastily putting on our road decks right now. That's going to be brought in on slabs like this. It's going to work down, and it's going to be highly corrosive to the steel if it's there. And if not, then freeze-thaw cycling is going to continue to work on that joint. We're eventually going to break a piece of concrete loose. So it begins with aesthetic, and it works onward from there. This is a really interesting crack to me. I had a contractor send this. This is a 1970s tilt-up building, and I had never seen a crack like this. This crack looks like a ladder truss as it snakes all the way up through this column between two panels. And it really puzzled us as we looked into this crack, and because the owner was looking to mitigate the crack as they were renovating the warehouse. They really weren't too concerned about it structurally, but they just didn't like the looks of it. But a structural engineer wanted some opinions. So we got to looking at the drawings, and back in the early 70s, this is down in Florida, one of the things that they liked to do, because they were worried about construction tolerances, is that they would set up the panels about 10 to 12 inches apart, and then they would come back, form the space, the gap between the panels, and pour it full of concrete, and they'd have steel bars that they would dowel into the two tilt-up panels to provide continuity. So the first thing that tells me is you've got a building here that's a couple 100 feet long that has no expansion joints in it. So you've got a 200-foot long concrete wall that's just growing and shrinkaging and growing and shrinking in the hot Florida sun with no movement relief. And so the concrete's going to find a way. And this concrete column, because the dowels that were into the adjacent panels, little by little began to get pulled apart. Structural concern? No, not in any way, because they're not relying on this column for the stability of the roof diaphragm working with the walls. But it is certainly as unsightly and an aesthetic. Could be a potential for leakage. In this particular case, the crack on the inside wasn't as significant, so they weren't getting water penetration. And it's also a crack width that I could put a coating over it that would span the crack and not allow water to get through. But it was an interesting study. I had never seen panels connected like that before, and a great study in cracking. So when we see cracking, some of the things that I'm looking for as I begin to look at pictorial examples, if I get a chance to go to the job site, or if they have me come out to the job site to do a look, or if I send a colleague, a structural engineer member, or someone else from our association out to see it, we're looking at the impact of the mitigation effort. What really needs to be done? What is the number one concern in this particular crack case that we have to deal with? Obviously, my last one, the replacement. This is a slab that needs replaced, but we're looking at conditions that affected the crack. If I've got a vertical crack on a foundation wall that's leaking, do I have proper surface drainage? Do I know that the drainage system is working? Do I need to run a camera down there and determine that the drainage tile was either cracked or damaged during backfill, or maybe it became clogged? It was a crappy system in the first place, or tree roots and other vegetation has clogged it up. Did it silt in? Those are things that can cause water to build up against these concrete elements. Is it waterproofed? First of all, if it was waterproofed, is the waterproofing breached? I got an example coming up here of a water. I'll tell you about waterproofing and how you can breach waterproofing when I get to it. And then what's the mitigation steps, or what are we going to do? Can we epoxy inject it so that we secure it? Can we keep the moisture out of it, either from the internal to the external, or vice versa? What are the methods for minimizing that crack development? Or can we mitigate or modify the concrete either in behavior or by a system belt and suspender, maybe, particularly in the case of a horizontal crack where there's bowing, that will minimize the crack and prevent further crack development? And then if we look at learning from cracks, again, looking at methods for minimizing the crack, reentrant crack corners, reinforcement. I'll show you that detail here in a little bit. Lowering the water content, right? We talked about that early on. Providing steel reinforcement. A lot of the idea of plain structural concrete is that I don't need structural steel. And yet I need steel reinforcement to control the volume change, the dimensional change, the shrinkage of the concrete itself, and providing construction joints in the right location. Those are just some of the recommendations that we have on a regular basis. Okay, so I've used up about 50 minutes. And so now what I'm going to do is I'm going to give you some, well, as best I can, some rapid fire. I'm a storyteller, and so I'll probably get into some stories here, but I'm going to give you some rapid fire examples, some other areas that maybe you'll commonly see, and we'll talk about some of the crack development. So slabs, I said it before, say it again, slabs are probably the most common for cracks. It's where we spend most of our time. We're constantly walking after them. The only thing that has lessened the influence of slabs being the most common area that we notice cracks is the fact that everybody's holding a smartphone now. And so half the time they're walking with their head down, their eyes are on their phone and not on the concrete. Before, it was always eyes on the concrete because you didn't want to look at the person coming to you. But cracking in slabs is significant. So we look at the techniques. I showed you this earlier. This is a shrinkage, a restraint crack. And so as this slab was shrinking, as it was changing dimensionally, going through its curing process, its ability to release itself, which should have been that horizontal joint that you see there, didn't happen. And so cracking is always going to follow sectional weakness. And that sectional weakness, as I said before, we can calculate it. We can determine based on the thickness of that slab, assuming that our tolerance is right, then we can determine where that crack's going to occur. Now, I can also use cracking to tell a contractor that they didn't meet tolerance on a slab. If I've got cracking that happens, a shrinkage crack, and it misses the intended joint by a foot or more, I can begin to calculate the slab thickness and tell them that in this particular area of the slab, they probably had a bulge in their subbase, and instead of being a 4-inch slab, it's only 3.5, or maybe it's 3 1/4. Sometimes I've seen slabs get down to 2 3/4 inches, and there's where the crack occurs. So it's almost always going to follow sectional weakness. In fact, I think it is always going to follow sectional weakness. Here's a graphic and then another slab image of the plastic shrinkage, the crazing, if you will. And so, again, this is a drying issue, as we said before. When you see the pure randomness, there is almost organic behavior in this cracking. It's plastic shrinkage or crazing cracking. It's an element of the surface of that concrete drying out too fast, losing its moisture content, and separating, in theory, from the volume, the thickness volume of the concrete slab itself. And so this is a cracking that will benefit greatly from a topical solution, one of the penetrant water systems that will seal the surface and grow crystals into those cracks to keep moisture out. Sectional reinforcement won't have anything to do. You cannot control this cracking with steel. You cannot control this cracking. You can start to control this cracking with fiber reinforcement, but if it's true crazing or plastic shrinkage, the drying is going to happen and the fibers themselves won't be strong enough to prevent those cracks from occurring. All they'll do is kind of help close them up or keep them from getting too extreme. So what do we do with slab cracking? We control it, first of all. And I know maybe some of you are involved in large logistics centers, warehouses, manufacturing facilities where the owners are looking for crack-free floors, and there's some massive structures out there. I've heard of up just under 1 million square feet of a warehouse slab floor with no joints in it at all, using a more elastic-based concrete and a combination of 3-dimensional reinforcement. So it's out there, it can happen. But still today, most of the cracking we control in slabs by proper controlled joints. The timing of those joints is critical. The depth of those joints, as I said, is critical. And here's an example of a proper slab joint. You can see when the slab is cut properly, the crack will occur really nicely right in that cut, and it'll go the full thickness of the slab. And as long as we've got a good base underneath this slab, we won't get any differential or displacement between the two slab sections, and that will be a lifelong slab that won't evidence any problem. If we don't cut that slab joint thick enough, then the crack may start in this, but inevitably it's going to find a weaker section. It could be in a piece of aggregate that causes it to start to head off in another direction until it finds a weakness.
Hey, Dennis, you've got a question.
Yeah.
So in slide 34, the image of the cracks do not extend to the edge of the concrete. We have seen cracks such as this in practice. Why would the crack not extend to the edge of the member?
I would say that it will. It will eventually. Now, if it doesn't, and I'll tell you an example where it might not. If I get a crack coming and I have an excessive amount of reinforcement. So one of the things that I hope to get to, I may be buzzing at that point, but you can get a concentration of reinforcement that is sufficient enough to stop the crack development, or at least to the human eye, hold the crack together to where you don't see it. Inevitably, concrete that if I look at this particular crack that's starting to warble along here, and my opinion is that it started on the right and worked to the left, is that if it had come from the left working over to this vertical slab joint, and let's say I had a couple number 4s running the length of that slab joint on the inside, on the left side and on the right side, that may have been enough reinforcement to seemingly stop that crack. And so if you're seeing a crack that kind of meanders like that and then stops, two things are going to happen. One, it's going to hit reinforcement to control it, or it hasn't been long enough. And generally speaking, the answer is it hasn't been long enough, and it'll crack through. Great question. Thank you for jumping in and asking that. Okay, I want to show.
Sorry, follow up if you want to.
Yeah.
Okay. What makes you think the crack started on a particular side of a joint?
Oh, good. Excellent question again. Okay, so again, if I assess a shrinkage crack scenario again, so if you look at these two cracks, what this tells me based on the dimension of the crack of the joints is that the vertical joint adequately separated the two concrete sections so that we're getting movement. If we're getting shrinkage movement in the vertical direction, and so as that, but the shrinkage that's moving, that's trying to compress the two slab sections on either side of that vertical joint, I should get relief from that horizontal slab joint. Because that slab joint's not thick enough, because it's a really tight line and it probably only went down, maybe 3/4 of an inch, maybe an inch. And it should have gone down probably 1 3/4 inches. So because that horizontal crack did not allow a cross-sectional thickness to relieve that stress. So then as it begins to pull on itself vertically, it creates friction on each side of that vertical joint, and that's where that crack ensues. So it's the roughness of the crack that's been cut and separates now is the friction component that starts the crack as it tries to stretch itself. Make sense? Now, where we'll also see this is when we've got, you can see this pretty easily also in a basement slab. Basement slabs are notorious for cracking because the slab itself is placed well after the walls, and oftentimes after the house is under construction. The first floor framing's on, and they're on closing up the house, and then they come back and pour the basement slab. And so as it begins to shrink, it's confined by friction along the side walls where it's trying to move laterally, and the friction against the wall, if you don't have an expansion material that friction along the wall is sufficient to cause the crack to develop based on where its friction exceeds the modulus of rupture of the cross section. And so right there where we've got that joint, the crack occurring, the stress from this crack off the page to the bottom, or off the photo to the bottom, is great enough to exceed the modulus of rupture. And then this section right here, I hope you can see my mouse moving, but the section from the crack up to where the two joints intersect, that's your friction component that causes that crack to get started. Okay, so on this slide, I just want to give you a picture for the stress that foundation walls are under, and that's really what I'm showing here. And ideally we've got soil capacity, we've designed to the soil capacity, and we designed to the soil pressure. And you can see in this image there's a grade line there. So from a engineer's perspective, you're assuming this, you're assuming that, and you're assuming the base. So there's three assumptions that you're making there about the design of that foundation wall, or at least the building code is making those assumptions. And so what happens oftentimes, first of all, is this grade does not get built or protected or maintained the way it should. Secondly, we have, as I said before, we have drainage problems, and so the soil lateral load increases beyond what we designed for. And in some cases, we can also get differential settlement underneath the footing, depending on the site that we're working with. And so these are some of the causes of structural cracking that can occur on foundation walls. Back to my vertical cracking, these are your shrinkage cracks. I showed them before. So you've got a vertical crack here. This one's an interesting vertical crack because to the right, you can see a tape measure there, and the crack is on the 2-inch mark. The form joint is on the 6-inch mark. And so this vertical crack is slowly moving closer to that form joint. So in this particular case, there was a weakened plane, probably based on the percentage of aggregate that was in that wall thickness, that allowed the crack to go up 6 to 8 inches away from from the form joint that should have been the weakened plane. Now, where this can also happen is if this, let's say, is a 10-foot wall, and I've got an 8-foot form, and then I stack a 2-foot form on it, and if I've got a filler that may be up there, a lot of times I can get the crack to start up in the filler's form joint, and then it propagates downward from there along a weakened plane before it migrates back to the vertical form joint itself. And then you've got a reentrant corner. So again, these are non-structural. The mitigation for these is a crack injection most often. It's a pretty easy fix. It's an ugly fix. And so then you got to figure out, well, what I'm going to do with the wall to make it look pretty again, particularly if I'm finishing the basement. But if I'm finishing the basement, I'm probably going to put a furring system and drywall in there. But this will lock out moisture. It'll also seal that wall back up so that there's no further crack development. The horizontal cracks, go back to that the drawing about the soil loads. This is where the horizontal cracks develop, is from a breakdown in the design of the wall versus the construction of the wall. And most of these, in my opinion, occur from means and methods problems, where the builder didn't allow the wall to be braced before backfilling. The backfilling wasn't done in lifts. They used a bulldozer and drove the bulldozer along the side of the wall and put an excessive pressure on the wall that began to fold it or put pressure more than what the vertical reinforcement and the modulus of rupture could substantiate. And so a lot of times structural augmentation is going to happen or going to be needed. Here's an example, though, of assessing the foundation wall cracking. If I see leaking going on the inside, if I start to see cracks that open up where they weren't before, and I come around the outside and I see something like this, obviously I don't have grade, negative grade or positive grade away from the foundation, and I've got water that is congregating and accentuating the soil pressure. And I might go from a design of 45 pounds per square foot soil load up to 60 or 70 or maybe even 75 pounds per square foot, and that wall wasn't designed for it. I get a moat that begins to build up around. Or here's an example. You can see the tracks from the equipment, and so they backfilled this foundation. Now, the geometry of this foundation might be okay. It's short enough walls that it might be able to handle full backfill, but not full backfill combined with the exertion or the excessive pressure of the cat that was used to drive this soil down in there. And I bet you anything, in fact, I can guarantee that they didn't put that in lifts. They just started pushing piles of dirt in and tamping it down. But it also shows you how hard it is in this condition to get a finished grade to move away from the slab. And so we could actually, along this short wall box that's in the middle frame of the picture, we could see some cracks, some horizontal cracks that show up. And there's one of those horizontal form lines that I talked about earlier. If I didn't have fillers that lined up, that's how I could get a crack that starts at a filler form joint at the top and then works away from the vertical joint in the bottom. This is an expensive correction. So you got two different options here. You've got they're digging out the foundation so that they can repair the drainage, waterproof it, put a dimpled sheet waterproofing, as well as maybe a spray applied membrane on that to keep the water from penetrating the wall. Now I've got a block wall on the right-hand side, but you can imagine if I had a concrete wall that was beginning to fold because of that excessive pressure, we might also have to use the piling soil stabilization system to hold that wall and keep it from bowing in further. So those are some of the expensive solutions that are out there. Let's move into tilt wall for just a little bit. This is such a common construction method throughout Colorado. And so maybe you guys have seen some of these examples. I don't have any Colorado projects here. I don't think. I won't guarantee that, but I don't think. So here's 3 different cracks scenarios on tilt-up panels. I got on the left-hand side, you've got some dramatic concrete cracks. Now, accentuating the cracks is the fact that they decided to try to patch it. And and then repaint it. And you had the bleached out, they used the same color paint, but it hasn't bleached out to match what the original paint was. And so these cracks are just blowing up aesthetically. But you've got these cracks that are diagonally moving up along the bottom of that panel. Now, what we know from these cracks is if you look at the vertical panel joints, it really tight against the upper left corner of the slide, just off the shadow image of the light, you can see a panel joint. And then that same frame in the upper right corner, you can see the other panel joint. And so if you just kind of look dimensionally about where those diagonal cracks start at the base of the panel, it's roughly at the somewhere between the fourth and the third points. That's where those shim stacks are. And so that's the point where the weight of the tilt-up panels bearing on the footing and the panels trying to shrink against those two shim stacks. The shim stacks are creating friction, and the structural engineer is supposed to design a trim bar using ACI 318 minimum steel ratio percentage, a trim bar, and you can calculate that stress of that panel of the concrete shrinkage and the friction coefficient off of those shim stacks. And without the trim bar in place, those panels will crack there every single time. And so that's one of the telltale signs of either improper or missing trim bar. Now, maybe the structural engineer designed a trim bar and the contractor didn't put it in, but in this case, those are trim bar crack. On the right-hand side, you can see it kind of looks like a square grid, a checkerboard grid on the face of these panels. And this is a classic case of this is an insulated panel job, much like that image right there. So you've got a thin architectural layer of concrete. On the right-hand side, you've got the structural layer and a complete separation of insulation in between. And on the right-hand side, that image, a lot of times they'll use steel reinforcement, steel mat reinforcement to reinforce that outside face for thermal movement. And the temperature, in this particular case, the temperature of that steel as this was built during the summer was had excessive heat in that face of that panel and caused cracking to map over the top of the steel reinforcement because of the curing, the rapid dimensional change of the concrete, much like crazing cracking that I showed you earlier, only happening on the downside surface of a tilt-up panel. So a pretty difficult crack to control, but it's one that's based on temperature of steel at time of concrete placement. And then this middle photo here is a horizontal crack in tilt-up panel, and I think I've got another view of that one in later, but I've got it in there to show you. So again, here's that the trim bar cracking. You can see it kind of moving up and away. It's not structural. It's not going to fatigue the panel in any way. And to the question earlier, they were talking the question about why did the crack not continue on all the way over to the panel joint? So it kind of stops at the shadow line of the light. It will continue across. Now, it is possible in some tilt-up panels. This one, not so much, because there's no opening. So you don't have concentrated reinforcement at the sides of the panels here like you would, say, more of a column and beam reinforcement for an office panel with multiple openings. And so there's not likely a concentration of vertical steel right here against the side of the panel. So my expectation is for this crack to continue to propagate over until it reaches the panel joint. Crack repair can be extensive. So, this is a reinforced drive-it coating that could be put on if the cracking is bad enough. In the case of this one, the right-hand side where the cracking does look to be bad enough, and you'd think, well, that owner is going to want to hide that cracks. Actually, what they ended up doing was they put a topical sealer on this, a penetrant that crystallizes in all of those cracks. And the only time they were seeing the crack is when the faces of the panels got wet. And by preventing the water from entering those cracks, they never saw them again. So that would be another way. Here's some of the reducing cracking that we're talking about. So here's reentrant bar reinforcement that should be in place. It doesn't matter what the construction. there should always be diagonal bars that are a minimum of 3/4 of an inch off of that corner, tied in place at a 45-degree angle that keep that crack closed, because it will start in the corner right here where that forming is. It will start, and once it reaches that steel, if the steel is sufficient, it will hold that crack closed and it won't continue to propagate. Talked about additional cracking. So we showed this condition earlier, the load cracking on the footing, and so the problem with those oftentimes are once the footing cracks like that, the footing can begin to rotate. If there's any kind of differential stress on the soils or differential pressure soil capacities themselves, those footings can begin to rotate or begin to shift, and you can open up panel joints. I saw that on a freezer facility several years ago where the contractor had cracked the footing because of the shim stacks and didn't grout soon enough. It went unnoticed until the freezer was operational, and they started getting huge ice dams opening up up in the upper sections of the panel joints, and it was because they got rotation in the footing because of the amount of cracking that occurred from the loads of those panels. And so one might say, well, there's no load at that crack because the shim stack is off to the left. When so that crack development right where it's at is more of a moment crack in that footing as it responds to the load that's being put into it by that shim stack. Over on the left-hand side, another one of the trim bar cracks that you can see coming off at a 45-degree angle. And this one, as you can see, has just almost, it might even have reached the panel joint before it finished. Once it gets to the panel joint, it'll stop. There's a close-up of the shim stack. Now this one's really tight against the side of the panel. That's a bit unusual. Most of the time, as I said, it's at the quarter points or the third points. Sometimes the fifth points. It kind of depends on what the preference is for the contractor. And the nice thing in this particular case is as they've got an embedded angle right here as well, and so they're getting some bearing on that embedded angle. But it's close enough to the edge of the panel that friction is not going to cause a trim bar crack to occur there. This is the grouting that's supposed to happen underneath those panels to prevent it from sagging or prevent it from affecting and cracking the footing. This should be done as soon as possible after the panels are braced to get the load off the footing on those single points. At the very least, if the timing of this is concerned, then we try to really teach to get multiple shim stacks pounded in underneath those panels and decrease the load applied to it. Here's an interesting project, a really nice project. It was a logistics center with a really nice office, 2-story office on one side of it. And the contractor got called back because of horizontal cracking that showed up. And so you've got a nice textured paint coating. Unfortunately, the owner opted for a cheaper paint coating, and so a proper elastomeric textured paint probably would never have showed these cracks, but they went the cheap side, and so the paint wasn't sufficient to span the crack, and the crack opened up the first time that they got thermal movement in that face. So again, this is a sandwich panel condition. Come to find out, in this particular case, the lifting design ended up using a higher modulus of rupture for its bending condition than what the contractor was prepared to deliver based on the schedule. And so it was a lack of communication between the, and this is all on the means and methods side, but a lack of communication between the bracing engineer, the lifting and bracing engineer, and the contractor for the time, the amount of strength, the maturity of the concrete at time of erection. And so the scheme that was used to lift these panels, concrete wasn't rigid enough, or the panel, think of it as the panel wasn't rigid enough, and it literally folded or began to fold. It's in theory or in moment began to fold sufficiently that a crack developed on the outside. And so these cracks, again, were pretty easy to calculate. What we ended up doing here is we brought in a consulting engineer that was that just looked, actually did a real quick look at the design and looked at the concrete strengths the breaks at the time of lift, and found out that the modulus of rupture was about 50% of what it should have been. And so horizontal cracking in tilt-up panels is pretty unusual, but it is certainly something that that would be a concern and needs to be looked at. So there again, I'm highlighting them just so you can kind of see where those horizontal cracks are, and they're purely vertical, which is a telltale sign that it was a bending stress in the panel at time of lift. This is a tilt-up panel that had water leakage. Again, you can see a reentrant corner. This is a tilt-up panel, not a foundation wall, but concrete doesn't care what got it there or what type of concrete section it is. And so in this particular case, we've got a crack that developed off the corner of this window, and we've got a crack. You can see this is a vertical. This is meant to look like a vertical reveal, but it's underneath a window. And in this particular case, where the vertical reveal is, what we found is that neither one of these were reinforced sufficiently. So the structural design of the panel was based on the full thickness to the left and to the right of this vertical reveal, and the vertical reveal reduces the structural thickness, and so they ended up with less than the amount of coverage that they designed over the steel reinforcement, and that was a weakened plane, and so cracking occurred there. Now, it's not a structural crack, but it's a crack that occurred that they couldn't control. And so it was a crack where moisture, it was bad enough, it went full thickness, and moisture was allowed to get in underneath the windowsill right here at the top of the crack that they couldn't seal off. Similarly, on this reentrant corner, when we did rebar analysis, we found that the reentrant bar crack, or the reentrant bar crack control, was about 3 inches off the corner where it should have been 3/4 of an inch off the corner. And so we had no chance, they had no chance to control this crack from the beginning. There's a larger image for you of that reinforcement mat pattern cracking of that project that they ended up sealing. This is not long after a rain, so the cracks are really showing nicely there, but like I said, they sealed it and are very happy with it. They still haven't painted the building. Here's another example of shrinkage cracking. Again, a tilt-up panel, and let's see, nope. So I think you can see from the efflorescence the cracking that's occurring here in this particular panel, and so this is more of a shrinkage crack getting established in the face of a panel. You very rarely see this in a solid panel, but it's not uncommon in the face of a sandwich panel. And so where these diagonals, this is a lot like the trim bar cracking we looked at earlier on the base of the panel. Now we're up at the top of the panel. And so where the coping is connecting, the coping is creating stress and friction, confinement of the shrinkage, and it's sufficient to start to crack the face of that panel, which is why those diagonal cracks are getting started. And so in this particular case, the treatment of that crack was the real problem, is they didn't get them sealed up properly before they painted, and so the paint coating cracked right over the top of them, and then began to effloresce as the water leached into the concrete and then back out again, because these particular cracks the water's not going to get into the inside because there's a structural panel and an insulation layer on the inside of it, but it's very unsightly on the outside. Now this isn't cracking. Yeah. Go ahead.
Real quick, we had a question back on slide 53 that were the cracks that were a result of the lifting stresses on the tilt-up wall. Yeah. Will those cracks typically show up on both sides of the wall or just on one side?
In this particular case, just one side. Again, this is a sandwich panel, and so the the modulus of rupture in the face panel. I also think, if I remember correctly on this one, they also decided that they designed for a stiffer section. They assumed that the full panel thickness would prevent bowing during the lifting, and so they put additional stress in that face. So no, in this particular case, these cracks were only in the face, the architectural face. you've got insulation, you've got structural panel behind it. And so these did not propagate through to the structural side. And because of that insulation layer that completely separates them, there's no force that would translate that crack into the interior panel. Now, I have seen what what you're questioning. I have seen structural panels with horizontal cracks on the inside, and those largely come from that same condition. But when you're dealing with a solid thickness panel, no insulated panel, and so it's generally when the modulus of rupture is assumed higher or counted on, or not delivered to the design specification, and you end up getting greater vertical flex, and it begins to fold. And so then in a structural panel, if that happens, or a single thickness wythe, you are going to get that crack that will propagate through to the inside face. Really good question. I threw this one in there because I just think it's funny. This is an example of obviously a failure on a job site. They had a spandrel panel that was up in the air, and it was being supported by these smaller leg panels. The leg panels weren't tied off, and the whole thing fell down. Now, what happened once they replaced these, what they didn't recognize, and the reason I threw it in here, is that up here on the left, where this spandrel panel is sitting against this panel with the large opening through it, is that it put enough pressure and warped that panel. So they actually had some cracking. You can't see it here, and they didn't even notice it until they cleaned up the panels. But it ended up putting a diagonal crack in the side of this panel where this panel was resting on it. So some cracks just happen. You can't design for that. You can't prevent that one, but it did happen. A lot of times my cracks come in from homeowners, and so this is just an example of a homeowner report on the right-hand side. They've got vertical cracks. This is a foundation. They're seeing this what looks like a really ugly crack. And so then they send it to me, their hair's on fire. I want to sue somebody. I want this basement torn out and replaced. And so we go through a process with them of helping them understand their crack, what's problematic, how can they fix it, what they can leave behind. I've taken a little longer than I wanted to get to this series of photos, but this is a project I was on recently. I had a builder or a contractor call me saying, hey, my builder, we normally do single-family residential units for this builder, and now we're doing fourplexes, and we're getting a lot of cracking. Can you come help us understand where we're getting cracking? Well, in ACI 332, which is the residential concrete code, there is a lesser amount of steel reinforcement required than what you see if you go through ACI 318. And one of the reasons for that is because the sizes are smaller. The maximum plan size are held tighter. And so concrete doesn't have as far to shrink. We're not developing as great stresses. But in this particular case, so we've got a vertical crack right underneath where it says Tyvek. There's a vertical crack. Now this happens to be a step down. So on the left-hand side, the wall's higher. On the right-hand side, underneath the window, or underneath the framing, it steps down. And so the grade is stepping down, moving from the left to the right. In talking to the contractor, they had no reentrant corner trim bars, nothing to prevent crack development. And so what they ended up getting in this particular case was, because it's a downward pressure on this step down condition, instead of the diagonal crack, they ended up getting it to go down a vertical plane, because you can kind of see it on the right hand side, just as the frame condition meets a vertical form seam, and there's a vertical form seam right here underneath the Tyvek, and so it was cracking right there. The other thing that's concerning to me here, look at where the soil is, and there's no waterproofing. And so the reason why they're getting water, which is really the reason why they called me out there, is they're getting water on this foundation, is because the waterproofing itself is below the grade line. Why? Because the builder didn't want to see the waterproofing. The builder is really concerned about the homeowners seeing black waterproofing versus gray concrete. So they intentionally try to hold the waterproofing down at the grade line. Well, it doesn't take a rocket scientist to figure out that somebody's missing what grade line means on the drawing, and they're over it by about 6 inches, because this is just rough grade. and they've still got more to go as they bring in the sod. And so they're getting water pressure down inside their waterproofing, which is back to what I said earlier about how waterproofing fails. This is an example of both a step down and a step footing condition, which is not too common, but it happens a lot on these walkout and daylight townhome conditions. And so again, they were missing the reinforcement. I've drawn the reinforcement that they should have in place. So the horizontal dashed line that you can see there, they had the bar that's right underneath the step down condition here to the top. They had the bar that's just above the step footing condition at the bottom, but they didn't have that middle bar because they were reinforcing to the single family residential code and not to the commercial code. And this wall length that we're looking at here is about 80 feet. The maximum plan dimension for the residential code is 60 feet. And so they've got more shrinkage occurring across this wall than what their steel is capable of holding. And so this kind of I can't augment that. I can't mitigate it if there's a crack develop, but I'm expecting a crack to develop right here on this form line that they can't control. So here's an example of the step down footing condition, reentrant corner. You've got reinforcing bars top and bottom. This is how we reinforce that step footing, and the footing is interrupted. We don't have to have a continuous footing here, which is a really excellent detail as long as that reinforcement's in place, and they're not putting that reinforcement in. They also got a crack along this wall, and this is the back side of the wall, and I'll show you a plan here in just a minute. But on the left-hand side, you can see right where the intersecting wall meets the long wall, they're getting a crack. And they're getting a crack at that point. Again, it's a filler condition. The form panel is full to this point, and then right where all the goop is, there's a small little filler that they put in because of the architectural dimension. And they did not have this lap splice developed properly, and so they couldn't control the shrinkage away from that weakened plane that is that form joint. And so it's an elementary condition to try to prevent. But here's a plan view of what in essence is I think that's like 240 feet or something like that is the dimension across here, this fourplex. And they were getting cracks at these intersecting walls where I've got the red lines, crack here, and then the crack I just showed you is right here. They were also getting that crack I showed you earlier is over here on this sidewall. And the crack development at these intersecting walls is all associated with the fact that you've got such a long wall across here. They had less than half of the amount of steel that you could calculate that they needed, that they required. And so the shrinkage was forcing crack where the points of restraints were, which are these intersecting walls. The builder was, not adversarial about it, but was certainly concerned. Hey, let's stop this if we can. And so we had to remind them what plan dimensions meant for maximum and minimum percentages of reinforcement and how they needed to reinforce per code. Oddly enough, I talked to the builder about why they hadn't had an engineer looked at this, and their comment, I quote, was, "Engineers are too conservative. They put too much steel in these things," which I thought was kind of funny because that's what the problem was, is they were missing the steel. So here's just a wall section. This is ACI 332 minimum steel. So you can see there's 3 horizontal bars here at an 8-foot wall. So that's a decent amount of reinforcement for these minimum plan dimensions, 40, 50, 60 foot. It's going to be sufficient. It's going to hold those cracks together. And the problem is, though, when you step into the commercial code, and so this is a wall section that's affected by the commercial code, not only do I have double mat steel, but that's the most economical way for me to get the steel percentage high enough to meet what ACI 318 says is my minimum amount of steel. And so you can see the 2 different layers, and this is I think this is an 8-foot wall also, and I've got 6 bars on each side, so 12 versus 3, because I'm accounting for the fact that the wall length is much longer. Here's another. This is really common, and one of my last conditions to show you, which is shrinkage that looks like load reinforcement. And so the concern that homeowners have here, you got this big steel I-beam here that's resting on this pocket or this ledge, and they see this big old crack that's propagating right at the corner where all of that load is. And they're thinking, my house is going to fall down because the steel column is going to fall away from the concrete wall. When in actuality, what's happened here, because this is this particular case is on a wall turn, so the wall is coming in from the left, turning and receding away from us in plane with the steel beam. But that the load of that steel beam is putting enough force into this section of the concrete directly underneath of it that as the concrete wall to the left is shrinking, and they did there, and this is really hard. This is probably one of the hardest places to put reentrant bar corner reinforcement, but there's no steel in here reinforcing this, and so it can't help but to shrink and crack. And so you can see it propagating down. Now this one may or may not, to that question earlier, will this propagate all the way to the floor? It may or it may not. My guess is at some point, even if it's a molecular level, that crack will proceed to either to this form joint over here, this form joint over here, or it might kind of continue all the way down. But it is reinforced underneath of it so that it's not going to become a structural concern. But it's hard to tell a homeowner, hey, that's a shrinkage crack. Your wall's not going to fall down. And then this is, I think this is one of my last one. Until I get to, I'm going to have to breeze through the resources. I know I'm keeping you just a little bit longer. I apologize for that. I thought this one was funny. This is an above grade concrete home. This is an old home. This one was done in the 60s. You can see the insulation. The homeowner called me. It had a fire, burned everything down but the concrete wall. And they called me and said, hey, we're really concerned about some cracks that we're seeing here on the outsides of these walls. I had to laugh because you can see, I mean, the cracks are created because the wall thickness changes. When they built this wall, they couldn't control that insulation, which it's really low strength insulation in the first place. But all of the cracking there, again, not structural, but certainly is a concern for the performance of that insulation. Okay, so where do you go? What other references are out there? How can you revisit this stuff? Brittany's recording this presentation, so I appreciate that. But some of the places, we've got several references out there. This is a tech note that we offer in cracking. We give this freely to the homeowners. You can get it on our website, cfaconcretepros.org. And it basically talks through a lot of these common cracking issues that we've been talking about tonight. And it shows you when's a crack to be a concern, what do I do with my crack, how should I investigate it? And then we pair that also with this tech note on waterproofing, backfill, and maintenance, because so many of the cracks are accentuated. If they're not caused by, they're accentuated by conditions of backfill, improper maintenance, or lack of sufficient waterproofing or improperly applied waterproofing. And so, excuse me, this one pairs really well with that. Subsequently, what contractors rely on, this is a technical hotline the CFA hosts, and under there's three different divisions, and under this technical hotline division, there's a lot of these photos that are shared. Contractor will share this photo and say, hey, we've got this callback. What do you think about this crack? And what would you do to it? And so there's a lot of sharing that happens in this particular resource. There's also the residential standard that I've talked about several times, the residential concrete code, and some of the detailing that I showed you is part of this standard. You can get it through aciconcrete.org, and this is referenced by the IRC as an alternative acceptable standard. It's paired with the 332 guide, and the guide itself talks about some of the differences between crazing cracking, concrete shrinkage cracking, plastic shrinkage, the stuff that we've talked about today. On the tilt-up side, they also have a forum. TCA's forum is at engage.tiltup.org, and you can see just a quick view here. Very similarly, there's different forums there, different topics. Members write in to share experiences. It's a great resource for asking tough questions and getting some really experienced responses. And I can tell you one of the things that I appreciate the most about these forums is invariably somebody says, hey, I've got this crack condition. What do you think? And the first half dozen responses is share some photos. We want to see it. It's amazing what you can learn from looking at photos and assessing, just as we kind of have been about quickly tonight, where cracks develop, why they develop, and what can we do with them. ASCC, American Society of Concrete Contractors, has a couple of position statements that might be useful. ASCConline.org is their website. This is a cracks and slabs on ground position statement that might be useful. It talks about random cracking, dry and shrinkage, a lot of the things, again, that I've talked about today. And then they also have a position statement for cracks in structural concrete and what are the concerns there, what are the repair, when is a structural width crack problematic, and then what resources. So that goes back to ACI 224 for how do you control cracking in structures and how do you mitigate or repair them. So everybody take a deep breath. I'm only 10 minutes long, which really is phenomenal. I'm normally like a 45-minute over kind of guy. But I appreciate your attention, those of you that have stayed with me. There's my contact information for both of my associations. Brittany certainly has it. And I really appreciate the opportunity I see somebody's taking a picture there. Let me put that back up. And by the way, it is in the handout if you downloaded that handout, but there's that slide again. But I'm available. The associations make me available for all kinds of consultations, references, resources. I enjoy, above anything else, talking through the eyes and the experiences of others in the industry. And I'd love to find out what projects that you're on and problems that you're facing. So once again, thank you very much for your attendance. Brittany, back to you.
All right. Thank you so much, James. I just wanted to see if there are any questions anyone has. If you want to type them in the chat box, give it just a minute here. And then I don't know, Katie, if you had any announcements that you were wanting to make.
Give me just a second. I was going to pull up some stuff. I know we've got a SEAC meeting coming up that should have some good content. Give me just a minute. Sorry, I'm so busy hosting the forum that nothing else will load on my computer. But again, there is the SEAC individual compensation survey went out earlier this week. So if you are interested in seeing how your individual compensation package is kind of comparing to those throughout the Colorado area, the only way you can get that information is to participate in the survey. So it's asking things about, you know, vacation time and 401k matching and all that kind of fun stuff. SEAC, you know, collects that data every year. It's analyzed by a third party, anonymous, that kind of fun stuff. So I know that's something that it tends to be of interest to our younger engineers. So I just wanted to encourage everyone to participate if you're interested in seeing the output of that survey. And thank you to our business management committee for putting that together. Again, all of that data is analyzed by a third party. Another fun thing is the younger member group is hoping to host the gingerbread bridge competition again this year. We'll be starting our fundraising efforts shortly. And the date for that was released in the newsletter last month. I believe it's the Thursday before Thanksgiving. And I would love to confirm that for you. But again, I'm having a really hard time getting any of the things that are in my email to load, so I apologize. Yes, thank you, Amber. The next SEAC meeting is May 20th on thermal bridging. So that should be a useful topic, especially
Great topic.
Yeah. So that's exciting. Let's see what else. Oh, and just another tidbit on the gingerbread bridge competition. We're not 100% sure what that's going to look like based on any COVID restrictions, but we're really hoping to be able to do that in person and just spread out a little bit more than we normally would be to have people be comfortable. But hopefully we can get it so we're not having to like stagger teams so that you don't get to interact with one another. But we're just gonna play it by ear and figure out what safety precautions we need to be taking. But we're really excited to get that back online for everybody. It's one of our favorite events of the year. So look forward to that. Amber, Brittany, am I missing any announcements? Anybody else on a SEAC committee who wants to plug something that we might be missing? See, Amber's typing. Yes, Amber, Friday, November 19th.
Yes.
Thank you.
Yep. It took me a while to find also, but that's all the announcements that I have, though. I think you covered it all.
Awesome.
All right, well, I think that wraps everything up. Thank you again so much, James, for the presentation. I guess we have one question here. How do we access recording for this presentation? I believe it will be on the SEAC website. Is that correct, Katie?
There will at least be a link. We are hoping to get some of this posted to SEAC's new YouTube channel, which we'll then provide links to, like on the SEAC website, so you can navigate that way as well. This will be like the third or fourth video that goes on our YouTube channel. So like, follow, subscribe, y'all.
I do have one more thing, Katie, and maybe you said this while I was trying to find some dates for you. But we are always looking for new members for the young member group committee. So if you're interested or you just want to chat with some of us a little more, feel free to reach out. It takes a lot of volunteers and a lot of work, but it's definitely rewarding. So if you're interested, reach out to us.
Yeah, and that you can do that via email. It's ymg@seacolorado.com, and I'll put that in the chat box also. Well, if nobody else has any more questions, thank you again, James. Your expertise was greatly appreciated. Thank you for sharing with us.
Yeah, my pleasure. Thanks for the opportunity. I hope to connect with you guys again. I've got lots of topics that I can always bring if you're looking for one filler.
Awesome.
Oh,
have
sorry
a good
about that. You didn't hear that. I just said, I can always come back and fill in another topic if you're looking for something. So don't hesitate to ask.
Awesome. Thank you so much, James. Well, have a good Thursday evening, everyone. Good night.